Okay, so let's recall what we were doing. So first, recall some notation. So E of Z means e to the power 2 pi I z. This means sum over A mod Q, where A and Q are co-prime. And so we had two theorems. So theorem 1, this was the additive large sieve inequality. So this says that, so suppose alpha R is a subset of R mod Z such that the points are delta spaced, so which means alpha R minus alpha S is greater than 1 by delta for some delta positive. And this, so the norm of some real number x means infimum of x minus n. Okay, so then the theorem says that sum over R A n e n alpha R square is bounded by some constant times n plus 1 by delta into norm S square. And this is for any sequence alpha. Any So this is a weaker version of the theorem. The stronger version will give you less than or equal to n minus 1 plus 1 by delta with c equal to 1. But we are not proving that. Oh, sorry. Delta. Here it is 1 by delta, here it's delta. Okay, and theorem 2, this is called the B large sieve inequality. This just says that sum of Q up to capital Q, sum of A mod Q star, so co-prime residue classes, this is bounded by same constants, maybe a different constant, no, the same constant, times n plus 1 by, now there is no this thing, times norm A square. Again, for all, this is, for all sequence n. And we also saw that theorem 1 implies theorem 2 by taking the set alpha R to be the set A by Q, where A and Q varies like this, with Q up to capital Q. And in this case, you can check that delta I can take to be 1 by Q square. And so therefore, we need to prove theorem 1, and we started proving it, and we were in the middle of proving theorem 1. So let's recall very briefly what we were doing. Proof of theorem 1. So by duality, enough to show the following, that so instead of this sum, I will have the dual sum. So the sum over n will be outside. And then sum of gamma r, E of n alpha r. And this should be less than or equal to C, n plus 1 by delta, norm gamma square, for any sequence gamma r. And one thing you should recall is that what is the size of this set of alpha r? So these alpha i's are, they lie on the, R mod z. I can think of this as R mod z. And the gap between any 2 points has to be at least delta. So the cardinality of the set of alpha r is at most, I think 1 by delta, or at most 1 by delta plus 1. To be safe, let's do this. So in particular, this is O of 1 by delta. So one should always keep this in mind. Okay, so these are the points alpha r. So we were proving this, and to prove this, we started with this sum. So S equal to this sum. And then we bounded it by, so here this sum was between m and m plus n. Then we bound it by sum over all n. But I plug in this smoothing factor, so n minus m by capital N. And then you open the square and interchange summation. So this will be R and S, gamma R, gamma S bar, sum over n, f of n minus m by n, E of n into alpha r minus alpha s. And then at this stage, the only thing to do is Poincare summation. So this step is Poincare summation formula. And that gives you, after you make change of variables, etc. So n times r s gamma s bar. And then let me check, I have forgotten. We should get so we'll have sum over m, E of m into alpha r minus alpha s minus m times f hat of n into alpha r minus alpha s minus m. Okay, that's Poincare summation formula will give you. And then we bounded f hat. So I choose a function f that dominates the constant function 1 in this interval, and it has a decay of the type fx is less 1 by 1 plus x square. So we discussed this in the last lecture, so I'm not giving all the details again. And then this gives you that S is bounded by Rs. Outside there is n, gamma r, gamma s bar. So I'm putting absolute value, so this exponential of something that will be just 1. And then I have sum over m, 1 upon 1 plus, what is it? N into alpha r minus alpha s minus m whole square. Okay. Okay, then I subdivide this sum. So recall alpha r minus alpha s can vary between -1 and +1. So for m which are close to this, namely when m is 0, 1 or -1, I bound it separately, otherwise I bound it in a different way. So this is n. Oh, so here I can put absolute value. And then here I do m outside -1, 0, and 1 plus m is, okay. So when m is away from alpha minus alpha s, namely here, I can just, we checked last time that this is bounded below by m square by 10. So then I can bound this sum by so this will be 1 upon, so yeah, let's put it this way. So m is greater than 1, 1 upon nm whole square. So this sum of 1 by small m square will be O of 1. And for this thing, I will bound this by norm of alpha r minus alpha s, so 1 upon, so this is here, and then alpha r minus alpha s square. I can ignore this one because, I'm getting an upper bound, so I can, if I decrease the denominator, I'll get an upper bound, so I'm dropping this one. And similarly, for when m is away from alpha minus alpha s, I am, sorry, this I want to keep 1, right. So let me write it again. This plus 1 upon 1 plus n into alpha r minus alpha s square. Yeah. Yes? Yes. Yes, that will be there. Yeah, that is there. So in fact, this part will be very small because it's 1 by n square. So let's take care of this part first. So let's call it S1 plus S2. So where S1 is n gamma r gamma s, and then you see S1 is less n by n square because the sum of 1 by small m square is bounded. And now I will just bound this by, so you just write it as sum over r, sum over s, gamma r square plus, right? Because AB is bounded by a square plus b square. So this is bounded by 1 by n, sum over r, gamma r square. Then just number of points s. A number of points s is 1 by delta. So this is 1 by n delta norm gamma square. So this is extremely small. So this will be absorbed in one of the terms. So 1 by n delta is much smaller than any of them. So I can absorb it in the, this O constant. So I don't need to worry about this part. So I will now handle the sum S2. So, yeah. So for S2 is bounded by, so n is there, and Rs. So again, I will bound this product by the sum of square. And for this part, so let's first write whatever is written. Okay. And then let's look at the first thing. So sum over R, gamma R square, and then sum over S, 1 upon this thing, plus a similar sum with the R replaced by S, but it will be exactly the same thing, so it's enough to take consider only one of them. So here I can write, so instead of S, you see so in this sum alpha R is fixed and alpha S is varying, and I know that in an interval of length delta there can be at most 1 point. So near alpha R there can be at most 2 points, in delta close to alpha R. So that constant is absorbed by this, so it will be of the form nk delta, where k varies from, so k from 0 to something like 1 by delta. I don't really need exact upper bound. Plus a similar sum, but it is absorbed in this thing. Is this part clear? Okay, and now you write it as, so this part I can pull out, so this is norm gamma R square, gamma square, norm square, and then sum over k, there is a term k equal to 0, which is the diagonal when alpha R equals alpha S, the difference is 0. So that will give you 1. Then I have sum from k up to, let's go up to 1 by n delta. So this sum may be vacuous, because if n delta is greater than 1, this sum is vacuous. And in this range, what is the size of this? So that's like 1. I can bound it by 1, plus sum over k greater than 1 by n delta. And here I can drop this one because I want this is an upper bound. So this will be, so I can pull out this n delta to the minus 2. One by k square and k greater than 1 by n delta. So this will contribute something like 1 by k with k equal to 1 by n delta, which is n delta. So I'll get 1 upon n delta, and here also I'll get 1 upon n delta. So finally, this tells you that S, so let's keep it because that's the statement. So S2 is less. So 1 plus 1 upon n delta. So there is a n outside. So this is n plus 1 by delta into norm gamma square. And we had S1. S1 was very small. So I can now put it, and that will be absorbed by this, so I don't need to worry about. So therefore, this is S1 plus S2, and this is n plus 1 by delta into norm gamma square, which is what we wanted to prove. This is the dual statement. So this proves theorem 1. So the proof is fairly straightforward. You use duality, then square it out and apply Poisson, and then estimate. Which step here? Okay. So up to this it is fine? That step, okay. So here what is happening is, let's forget this. So I have only gamma R square and then this sum. So here R is fixed. So S is varying. So I have some alpha R here, let's say. Okay. So alpha S can be at various points. So it can be distance delta from alpha R, distance 2 delta from alpha R, etc. But in any interval of length delta, there can be at most 1, because if there are 2, then they won't be delta spaced. So as you go from 0 to delta, delta to 2 delta, 2 delta to 3 delta, you can have at most finite, bounded many. So the gap is increasing by, so I start from alpha and then start counting 0 to delta, then 0 to 2 delta, etc. At each step I have bounded number of things, so we get this sum. And k cannot be too large. K is at most 2 of 1 by delta. Okay, so this proves the additive large sieve, and we saw that the so-called P large sieve inequality follows from the additive large sieve. And now I go to the arithmetic large sieve. So, okay, so what is arithmetic large sieve? So first of all, what is a sieve? Okay, so let's say A is some subset of Z, and let's say P naught is a subset of P, which is a set of primes. And suppose for every prime in P naught, there is some subset omega p of the residue classes Z mod Pz, is a proper subset, which are specified. And then we want to sieve out the integers which, if you reduce mod p, should not lie in omega p. So we want to estimate the size of the set SA P naught omega, which is by definition those A in A such that A mod P should not lie in omega P for every P in P naught. This is called the shifted set. Okay, and why do you want to count it? What is the interest? So for example, in the usual sieve, what happens is so A will be some interesting sequence. So in the usual situation, which means not large sieve situation, P naught I can take to be the set of primes smaller than Z, and omega P to be just a singleton 0. Then look at this definition. This is counting those numbers in the set which are not divisible by primes P that are smaller than Z. So that means the elements that survive here can only have prime factors which are larger than Z. And suppose I am able to take Z quite large compared to X to the 1/3, then that means that these integers cannot have too many prime factors. There will be at most 2 prime factors and so on. So you can get almost primes from an interesting sequence A if you have this choice. But in large sieve situation, this omega P is going to be quite large. The size of omega P will be like a fraction of P, like P by 2 or something like that. So let's state the theorem. So this is why they are called large sieve, because the sets are large. So I should write so this choice will imply only integers whose smallest prime factor is greater than z survive in this S A P naught omega. Okay. Okay, so now to state the theorem, I need some notation. Okay, so let's suppose omega p is the size of capital omega p, and that has to be smaller than p. And let hp equal to omega p divided by p minus omega p. Okay, so all these things are taking place for primes p in p naught. And let h capital Q be defined as sum over hq, q up to capital Q, q square free for any q. So if some prime shows up that is not in P naught, H will be defined to be 0. So only the primes in our initial set will matter. Okay, so with this notation, the main theorem says the following. Oh, of course, I have to say what HQ is. So you extend, so where HQ is the product of HP. So it is extended multiplicatively. So I specify it at primes, and for other integers, it will be extended multiplicatively like this. Okay. Theorem 3. This is the arithmetic large sieve. Okay. So suppose F is a sequence from Z to C with support in the set S, which is just a shorthand for S A P naught omega. Then Fn So this is only supported in S, so it's a sum over integers in S that is bounded by q square plus n upon hq into, what is it? Yeah, norm f square, where norm f square is, as usual, sum of Fn square. And a corollary is if you take f to be the indicator function, corollary. So you take f to be the indicator function of S, then the left hand side will be size of S squared, and the right hand side is q square plus n by hq times size of S. So cancelling size of S, I get and all these results are for every q. So capital Q is arbitrary. So I will choose according to my according to my wish. Okay, and so I need, so first let's state a lemma that will immediately imply this theorem. Okay, is the statement clear? Okay, so lemma is due to Montgomery, and Terence-Tao calls it Montgomery's uncertainty principle. So this says that with the same notation, so I'll have two statements. One, HQ f at 0 square is less than or equal to a mod q star f at a by q square, and 2 HQ at 0 plus t f at t plus a by q square, where f at is exactly as Surya defined, but I normalize it differently, so there will be plus sign. E of nx. Okay, so first let's see that 1 implies 2. That is trivial, so note. Yeah, so this is clear because we can apply 1 to the function g, say, so gn, which is fn times e of nx, nt, right? So, so g hat of 0 will be just e of, f hat of t. Okay. So 1 implies 2. And 1 also implies the theorem because you simply sum over q. You see, you assume this statement, then you sum over q. This thing doesn't depend on q. So when you sum over q, this will just come out. So sum over HQ, that will capital HQ. And that's what is just a second, I may have made a mistake somewhere. No, it's fine, because you see, so yeah, so let's see. So lemma implies theorem. So sum over q up to q and apply theorem 2, which was the large sieve inequality. So if you sum over q, you will get capital HQ times this. And when you sum over q, this is precisely what, see, this is summation an e of na by q. So I can apply the arithmetic large sieve, and that will give you the bound q square plus capital N times norm of fn square, sum of fn square. So this immediately gives the theorem. So therefore, we only need to prove lemma. Is that, are you following what's happening? Okay, so how to prove the lemma? So I just need to proof statement number 1. So, okay, so I start with f hat of 0. So what is f hat of 0? It's just sum of fn. So call it sum of nu mod q x nu, where x nu is sum over fn, n is congruent to nu mod q. And now note that x nu is 0 if nu is in omega q. So assume q is a prime. So first assume q equal to prime. Then we will generalize it. So if nu is in omega q, then x nu is 0. And therefore, this sum is actually over nu not in q. So let's keep that in mind. Okay, and now write f hat 0 square equal to nu mod q x nu square. And I want to use Cauchy-Schwarz here. So it will be sum of 1 square times sum of x nu square nu mod q. And here, instead of writing nu mod q, I can write nu does not belong to omega q. Of course, nu is z mod qz, but it need not lie here. I mean, I don't want to have some extra terms here because the x nu was 0. So I'm using this observation. And that is same as q minus omega q times this sum. Okay, so I need to evaluate this sum. So I can now erase this, I think. Yeah. So what is this sum? Okay, so let's start with x nu. So this is fn, n congruent to nu mod q. This you can write as sum over all n, and then you capture this arithmetic progression by additive character. So this is 1 by q, sum of e n minus nu into, let's say, a by q, a mod q. Okay. So if n and nu are different residue classes, then the sum will be 0. And if they are same, modulo q, then I'll get q. So if I divide by q, I'll get 1. Okay, and this, you rewrite it as 1 by q, sum of e minus nu a by q, sum over n, fn e n a by q. This is sum over, this is sum over a mod q. So this is 1 by q, sum of a mod q, e of minus nu a by q, times f hat of a by q. That is the definition of f hat. Yeah, so f hat x. And now I have to take sum of squares of that. So for simplicity, let's call it CA. So this is 1 by q, a mod q, CA times e of minus nu a by q, where CA is f hat of a by q. So I want to keep this because that's what we want to prove. So let's continue here. So I want to evaluate this sum sum of x nu square. And what is x nu? X nu is that thing. So there is a 1 by q summation Ca E of minus nu a by q. So this is 1 by q square, sum of nu q. Then we just open the square as before. So that's always the trick. A and B, Ca Cb bar, E of nu into B minus A. All right. Yeah, B minus A by q. And then you interchange the sum. So 1 by q square, sum over A, sum over B, Ca Cb bar, then sum over nu mod q, E of nu into B minus A by q. Then again, this will be 0 unless B is congruent to A mod q. But here A and B are varying mod q. So they are equal only when B equals q. So that means I'll get q and A has to be equal to B, otherwise I'll get 0. So that means q by q square, A mod q, Ca square. Okay. So I can plug this in now. So this is q minus omega q into 1 by q, then f at A by q square A mod q. Okay. And that's same as 1 minus hq. Oh no, that's not true. Yeah, so let's keep it like that. Okay, and where were we? We were bounding this thing. So we have got up to this point. Okay, and now, so now we can erase. So one remark is that this calculation that we did, that this is same as this is essentially Parseval on the group Z mod QZ. So once you normalize things properly, Parseval will give this. But here it's very elementary to calculate. Okay, so now we continue from here. So we started with this, and we got up to this. Now we write so this is 1 minus omega q by q, and then sum of f at. So I'll separate the zero residue classes. So I'll get f at 0 square plus A mod q star f at this. Now I have an f at 0 square here, and I started with f at 0. So I'll take that f at 0 square to the left hand side. So that means f at 0 square into 1 minus, no, I have to divide by this thing. So 1 upon 1 minus omega q by q. And that should be less than sum of A mod q star. And that's precisely the lemma, because once you simplify this, you get exactly HQ. I think that's what the lemma says. Yeah. So that proves the lemma when Q is a prime. So we continue. I can now erase this. So this proves Montgomery's lemma. When Q is a prime. So I have to prove it for general square free integer Q. See, if Q is not square free, it is trivially true because then H is 0. So suppose, so we induct for a general square free integer Q, we induct on the number of prime factors on omega of Q, which is the number of so let's say I know it for so suppose lemma is known for Q with omega Q equal to R. And so let now Q equal to Q1, Q2. Where Q1 is a prime and omega of Q2 is equal to R. So if I can prove it for Q, then by induction I have the result for every square free Q. Okay, so I start with the right hand side. Now, so there's this. I use the Chinese remainder theorem, so that implies that any residue class A, so A mod, any A mod Q, mod Q1, Q2 can be written as A1 Q2 plus A2 Q1, where A1 is modulo Q1 and A2 is modulo Q2. So Z mod Q1 Q2 star is Z mod Q1 star direct sum Z mod Q2 star, and that gives you this. So I do that. So then I can write it as a double sum, A1 mod Q1. So here, and if A is coprime with Q1 Q2, so that is equivalent to saying A1 and Q1 are coprime and A2 and Q2 are coprime. So this will be like this. Then F at. So A is now A1 Q2 plus A2 Q1 divided by Q1 Q2. Then you have square. And this is F at of A1 by Q1 plus A2 by Q2. Okay. Now what to do? So you forget this sum. And you consider this as a constant. So this is like, you can write it as sum of A1 Q1 star. So don't do anything. A2 mod Q2 star. So think of it as G hat of A2 by Q2. Well, G is just Gn is Fn times E of n A2 by Q2, n A1 by Q1. So it's just a shift. Then G hat of this is precisely F hat of this thing. So apply our induction hypothesis that for Q2, omega of Q2 is R, so I can apply this result. So therefore, this sum is greater than or equal to. So here I am going to apply, so I will get HQ2 times, so this thing I have not done anything, so sum over A1. And for this sum I will get HQ2 times G hat of 0. But G hat of 0 is nothing but F hat of, what was I writing? F hat of A1 by Q1. And Q1 is a prime, so I can apply the lemma. So therefore, this is greater than HQ2, HQ1 times F hat of 0 square. And this is, by definition, H is defined multiplicatively, so this is just H of Q. So that by induction proves the lemma, and we have already seen that the lemma implies the theorem. So that proves the arithmetic large sieve inequality. And then our next thing is to do some application. So one application will be to the restriction theorems for primes that will be used by Surya in his course, I think. And another I wanted to do, but I don't think I have enough time to do the theorem of Linnik about least quadratic non-residue. So maybe I state the theorem and tomorrow I will prove it. So one application. So this is. Okay, so this problem is due to Vinogradov. So Vinogradov asked, or maybe conjectured that that if you look at the minimum of integers such that n by q is -1, and that should be quite small. So where q is a large prime, and I hope everyone knows this notation. This n upon q is the quadratic residue symbol, the Legendre symbol. So this means that there is a solution to x square equal to n mod q. Okay, so this is wide open, and usually this is approached by bounds on character sums. But Linnik proved that this kind of result is kind of true for almost all primes. So the exceptional set is very small. And that's a very typical application of large sieve. So let's state the theorem. Okay, so theorem. So Linnik was the father of the subject, the large sieve, and it was developed by many other people, Rennie and Montgomery, Davenport, Montgomery, many other people, Selberg, and so on. So let epsilon be given. So the number of primes p up to n such that n upon p equal to 1 for every n up to n to the epsilon is bounded by a constant C epsilon. So suppose Vinogradov's conjecture is false, what would that mean? That would mean that there are n, if you go up to q to the epsilon, it may happen that all these n by q are plus 1. And this theorem is saying that the set of such primes is very small, it is bounded. So if Vinogradov theorem fails, it fails for a very small set of primes. So this large sieve usually gives this kind of bound on an exceptional set. Okay. So it will take some time to prove it, so I think it's better to stop. I have still 2-3 minutes left. Thank you.